And there we go. All right, OBS is working, so we can get started. Who do we have in the chat? Okay, so Vanessa had asked for number 5 and 6, and then I think it was Kevin had asked for number 7 and 8. So we'll do those first. But if you have any other questions or topics, feel free to just post them in the chat, and I'll get to them. And like I said, I'll be here till 9, so we should have time for everybody's questions to be completely exhaustive. All right, so let's start with this. Okay, so we have f of x equals x ln x over y plus x y squared. Calculate f xx and f yz. So these are the derivatives of f with respect to each of these variables. So a f of x, y, I'm going to assume it also means z, because otherwise it doesn't make sense to do the partial derivative with respect to z. Right, z needs to be a variable if I want to do the partial derivative with respect to it. It could also be a typo, it could also mean x, but we'll do it like this. Actually no, I'm going to assume that's a typo, because otherwise this thing is just 0. So I'm going to assume that that's an x instead of a z. So this is equal to x ln x over y plus x y squared. So we want to compute f x x. So this is the derivative with respect to x of the derivative with respect to x. And f y x. So this is the derivative with respect to y of the derivative with respect to x. Okay, so first thing we should compute is df dx, right? This is fx, which is the derivative with respect to x. So first term, I need to use the product rule. So this is going to be ln x over y squared, nope, just y, plus x 1 over x over y times, so that's, I have to use the chain rule, 1 over y, plus derivative of the second term, this is just going to be y squared. So to simplify this, I get ln x over y plus the x's cancel out, and the y's are going to cancel out, so I'm just going to get 1. Right? Those cancel out, and these are also going to cancel out. Okay, and that's the partial derivative with respect to x. Now we can compute the partial derivative with respect to x of this. So this is going to give me 1 over x over y times 1 over y. The 1 over y's are going to cancel again. And then those don't depend on x, so it's going to be 0. So this is just going to be 1 over x. And I can also compute the derivative with respect to y of the derivative with respect to x. So this is going to be, let's see, so I need to do 1 over x over y and times the derivative of what's on the inside. Now remember, this time I'm doing the derivative with respect to y. So this is going to be negative x over y squared. And then plus 2y. And we can start canceling things out. The x goes away, and then one of these y's goes away. So what we end up with is negative 1 over y plus 2y. And actually, we can check if he meant with respect to z, because if that's the case, then this will be 0 for the answer. Yeah, no, it's this. So that right there should be a z, and we can see that right there. Or sorry, should be an x, and we see that right there. 1 over x, and that's correct. Okay, next part is determine the directional derivative of f at the point 2, 2 in the direction of the vector 1, minus 2. Okay, so for the directional derivative, let's append a page. Let's append a lot of pages. So for the directional derivative, remember the way we do this is d hat dot gradient f x y. Okay, so d is the direction vector and it needs to be a unit vector. This is obviously the gradient at the point x, y. So it gives us the function and we can figure out the gradient. So the gradient of f at xy, we'll plug in 2, 2 in just a second. Actually, let me copy the question down. Just so that I can have it in view. Okay, and our function, well, actually, so this, we already did the x derivative. We found that that was this, ln of x over y, ln x over y plus 1 plus y squared, right? Yeah. And now I need to do the partial derivative with respect to y. So I'm going to copy this real quick. And put that over here. And we want the partial derivative of that with respect to y. So df dy, that's going to be, so we don't need to use the product rule here. We have x 1 over x over y times chain rule x over y squared. Start canceling stuff out. We have this cancels, and we want the derivative with respect to y, so we have 2yx. Simplify, and we get minus x squared over y. Nope, not x squared, just x. Plus 2xy. And that's our y component of the gradient. Okay, so for the question, we need the gradient at the point 2, 2. So gradient of f evaluated at 2, 2. So this is going to be ln of 2 over 2 plus 1 plus 2 squared minus 2 over 2 plus 2 times 2 times 2. So simplifying, this is ln of 1, which is 0, plus 1 plus 4, that's 5. And here, let's see, so that's minus 1, and that's 8, so we have 7. Okay, so that's the gradient. Now I need to work on this unit vector. So it gives me the direction vector, 1 minus 2. But that's not quite what I need. What I need is a unit vector in that direction. So let's make a unit vector out of this. Let's compute the norm. Square root of 1 plus 4 equals root 5. So I can do, I'm just going to write it this way for now to save some writing. D over norm D dot gradient f at 2, 2. So that's going to be, 1 minus 2 divided by the norm dot product with 5, 7. So I'll do the dot product first, and this becomes 5 minus 14 over root 5. That's minus 9 over root 5. And that's my answer. Next question. Actually, let's check if that was right. Yep, minus 9 over root 5. Next part, let's copy that. Okay, suppose that x is this and y is this. So, okay, so this is asking for the chain rule. Yes, this is a chain rule. And let's move f down here again as well. And I'm also going to want the gradient, and we'll see why. Okay, so df dt. So I'm going to use, we can think of, I'm going to use the chain rule. This is the chain rule. So I do df dx, because I know how to compute that, and then I can think of multiplying and dividing by dx. So I do it for x, and then I also have to do it for all of the other variables. d whatever dot d whatever dt. So the only other variable in this case is y. If I would have had a z, I would have kept going. If I would have had more variables, I just keep going. Okay. So here, we know what df dx is. We've computed that. That's the x component of the gradient. Um, let's copy the gradient. Do I have room for this? Let's make room. Cannot see that. Okay, that'll have to work. Wait, am I in the wrong chat? No? Okay. Okay, so df dx, that's this. So this is ln x over y plus 1 plus y squared times dx dt. So dx dt, I'll compute that separately. dx dt is equal to, that's going to be, we have to use the product rule, so that's s t e to the t plus s e to the t. So it's this times s, or sorry, let's go, yeah, so this times s e to the t times t plus 1. Then I have df dy. We know that this is minus x over y plus 2xy times dy dt. And this is just 2s e to the t. Okay, so I'm not done yet though, because one, I should multiply this out. and see if anything simplifies. But 2, I need this whole thing in terms of s and t now. So I need to compute the turn the x and y's into s's and t's. So we know what they are, we just plug these in, and then I'm done. So df dt is equal to, so we have ln of x over y plus 1 plus 2s e to the t squared multiplied by s e to the t times t plus 1, comma, and then I have minus s t e to the t, and then 2s e to the t plus 2 st e to the t, and then 2s e to the t, all that multiplied by 2s e to the t. Is that right? dy dt, yeah, okay. Okay, so I had to split it into 2 lines, but there we go. So we start canceling stuff, and this becomes ln, see the s cancels, the e to the t cancels, we have 2 over t, or t over 2, plus 1 plus 4 s squared e to the 2t times s e to the t plus 1. Okay, and then here the e to the t's cancel, the s's cancel, and we have minus t over 2 plus, let's see, so we're going to have 4 s squared e to the 2t times 2s e to the t. And then finally, I'm just going to distribute each of these. So it's ln t over 2 s e to the t plus 1 plus s e to the t plus 1 plus, so we have 4 s cubed e to the 3t plus 1, comma, and the next term is going to be, let's see, the 2's are going to cancel, so we have minus t s e to the t plus 4 times 2, that's 8 s cubed e to the 3t. So I guess I could, is that going to fit? That might fit. Oh, wasn't that long. Oops. Let's try that again. There we go. Let's see how the answer was supposed to look, because that looks awfully long. Oh, I'm sorry. This is not a vector. This was supposed to be addition. Okay, same thing still holds. But this is not a vector. df dt is not a vector. It's supposed to be plus. So this whole thing is supposed to be added together, right? Because it's df dx, dx dt plus df dy, dy dt. Um, let's see. Parentheses, there we go. So this is added, and this is also going to be added all added together. I don't think anything simplifies though. S e to the t, so we have s cubed. I guess this term could simplify, yeah, I guess it can simplify a tiny bit. So here, if I write this as 4 s cubed e to the t times 2, when I can combine that with this term, and that'll change to a 3. And then I can also factor out some stuff here, and I'll do the same trick here. So I have s minus t. Okay, so that's actually going to cancel this out. S e to the t, and then plus 4 s cubed e to the 3t and t plus 3. And finally, yeah, I think that's fine. You could factor some stuff out just to make it look nice, but I think that looks fine. All right, you can factor the s e to the t out. You know, why not? Why not? S e to the t times ln t over 2 times t plus 1 plus 1 plus 4s squared e to the 2t times t plus 3. And that's my answer. Let's see, Kevin says, so I don't think we will have problems where we plug in variables, right? Only numerical answers for, yeah, probably, because it's a lot harder to like, especially if it's like electronically graded. Um, trying to determine what's equivalent or not is just a pain. So it's probably numerical answers. Or I'd say it's probably the same as all the other ones. I don't expect it would be any different. Well, I hope it's different than the last one because that was a mess. But yeah, let's see. So last part, question 5. Determine the equation for the tangent plane, for the plane tangent to the surface, this at the point that. Okay. And I'm going to need the function again. Actually, I don't need the function. I just need the, no, I need the function. Okay, so for this one, what we're going to do is we're going to consider actually the function g of x, y, z, and that's just going to be where I move everything over to one side. Okay, so when I move everything over to one side, well, everything except for any constants, but there's none in this. So this is going to be z minus f of x, y. Okay, and then my tangent plane is going to be gradient of g dot x minus x0, y minus y0, z minus z0. And this isn't actually so hard to compute because we already know df, df dy, df dx, and all that. So let me copy those down because that's really all we need. Okay, gradient, there we go. Okay, so I know that the gradient of f looks like this. So if I want dg dx, then that's just going to be negative. So this goes away, right? That doesn't depend on x. And that's going to be negative whatever the x component of the gradient of f is. And similarly, dg dy is going to be negative df dy. And also dg dz is just going to be 1. And of course, x0, y0, z0, that's going to be this point right here. So gradient of g is negative ln x over y plus 1 plus y squared minus x over y to xy 1. And actually, I forgot to mention this. I need this at the point 2, 2, 8. And we've evaluated this already. This was 5 and 7, right? That's what we had up here at the top. Part 1. Yeah, 5, 7. Except now it doesn't have 2 components, it has 3 components. That is not an 8, that should be a 1. Okay, so I do this dot product and I have this is going to be equal to 0. That's the tangent plane. So I'm going to have 5 times x minus 2. Oops. Yeah. Plus 7 times y minus 2 plus z minus 8 equals 0. And that's the equation of the tangent plane. Let's double check that it's right. Yes. Negative. Oh, he just has the negative signs. Oh, yeah, yeah. So this was for the gradient. I need the negative of that because remember I have these negative signs. So those should actually be negative. That should be negative and negative. And that should be positive, negative, so those are negative. So this is negative and negative. Okay, where do I get the 1 from? So the 1, so what I need to do is I need a function that describes this surface, this plane, the tangent plane, okay? G of x is going to be basically a level set of some function, but we know that the gradient of this is going to be orthogonal to its tangent plane, okay? So what I do is, and I have a function like this, I'm going to move everything over to one side, all of the variables over to one side, and set that equal to z. I'm going to move all of the variables over to one side and all of the constants to the other side. So for example, if I had like x squared plus 2y equals 3, suppose, or minus 3. Right, this is my f of xy. So I set up the function z equals f of xy, and then I'm going to move all of the variables over to one side and all of the constants over to the other. So I'm going to have z minus x squared minus 2y equals minus 3. And really it doesn't matter if you move this over or not, it's going to vanish. So when I do the gradient of this, the 1 is going to be the dg dz, right? Because if I do the gradient of all of these other terms with respect to z, there's no z there, right? It's just all in terms of x and y. So when I do the gradient with respect to z, it's just going to be a 1. Okay, so that was all of number 5. Any questions about gradient and tangent planes? I can pull up some more examples if you guys want. Or I can move on to question number 6 from the review. Chat doesn't say anything, so I'm going to assume number 6. Because this one's also the same or similar. Where's that coming from? Oh, that's from there. Okay. Yeah, so looks like this is a very similar one. Determine the maximum directional derivative of f at the point 1, -1. I should probably do this down below. Let's copy that down here, a little bit smaller. Okay, and we need that function. Okay, find the maximum so the maximum directional derivative happens in the direction of the gradient. So I'm going to need the gradient of f, no matter what I do. So this is going to be derivative with respect to x is 2y² plus 0 plus 4xz. And then that's going to be 4xy plus 2z². That's 0. Then derivative with respect to z, that's going to be 4yz plus 2x². Okay, and let's evaluate that at the point 1, -1, 1. So that is 1 plus 4, and then I have -4 plus 2. That should be 2 in front. So that's -4 plus 2, and then y times z, that's going to be -4 plus 2, which is 6 minus 2 minus 2. All right, so this is the direction that the maximum derivative is in. Okay, it's not necessarily the unit vector in that direction, but what we want, let's see, find the determine the maximum directional derivative. Yeah, so the maximum directional derivative is going to be the norm of this vector. So this gives us the direction, and the length is also the magnitude. So let's do the magnitude of this. That's 6 minus 2 minus 2. Square root 36 plus 4 plus 4. It's going to be 2 root 11. Let's see if that's right. Root 44. Yep. Okay, so again, what that means is out of all the directions, this vector right here, the gradient at whatever point, let's see, erase, come on. So say we're looking at this point right here, right? I could do a directional derivative in any direction that I want, but the one that's going to have the steepest derivative, the steepest incline, is going to be the one that's in the direction of the gradient. And the magnitude of that is going to be the slope in that direction. Okay, part B. Let's see, part B. Okay, and also need the function. Find the directional derivative in the direction parallel to the line here. Okay, so let me just rewrite this line in a way that's a little bit more familiar. So we have r of t is equal to 3 plus 4t, 2 minus t, and let me write 0 plus 3t. So this is going to be 3, 2, 0 plus t times 4 minus 1, 3. So I hope you guys recognize that this is the direction vector. So that's the direction vector. So that's the direction that we want this in. Now it's not a unit vector. We have to make it a unit vector just like we did before. But we do the same thing. Now we want to find the directional derivative dot gradient of f at the point minus 2, 1, minus 1. I know what the gradient is. I just computed that up here. Come on, select. Okay, so let's copy that down. So I want d hat time dot product with the gradient at minus 2, 1. So let's evaluate what that is. The gradient of f at minus 2, 1, minus 1. So this isn't the same before because we have different points. So this is going to be 2, and then we have 4 times 2, that's plus 8. And here we have 4 times xy, so that's going to be minus 8 plus 2. And we have 4yz, so it's going to be minus 4 plus 2 times 4, which is 8. This becomes 10 minus 6 and 4. All right, so that's my gradient. Now I need to look at this direction vector. So that's d, and I need to make it into a unit vector. Or I can just divide by the norm afterwards and save myself some writing. So I need to know that, let's see, let's scoot this over here. So this is 16 plus 1 plus 9 which is root 26. So this is going to be the same as d over norm d, right? That's how we make a unit vector, dot product with gradient f at minus 2, 1, minus 1. So this becomes 4 minus 1, 3, dot product with 10 minus 6, 4, all divided by root 26. Oh, that's hard to do. Nope, that's not right. So I can write on this tablet that I have, but drawing a straight line is like impossible. Okay, so I do this dot product, and what do I get? I get 40 plus 6 plus 12 over root 26, which is, that's 46, 58. And would that cancel? I don't think that would cancel, would it? Half of that is 29. Yeah, that's not going to cancel. So, is that the right answer? 58 over root 26. Boom. All right, part C. Determine the symmetric equations for the line normal to the surface. Okay, at the point this. Okay, so again, we're going to need the gradient, but this is very similar to finding the tangent line though. Okay, so before, instead of finding the, we had this gradient of g. This was for the tangent plane, x0 plus y minus y0. Right, this is what we had for the tangent plane. No, this was a vector. Now, so this was our normal direction. This was our kind of the normal for the plane. And then the x0, y0, z0, these were points on the plane. Okay, so we had this equal to 0. So this was the equation for the tangent plane. For the normal line, it's going to be very similar, except we're going to have, let's put this as r of t. We're going to have our point on the plane, right? This is just going back to how we do equations for a line, plus our direction vector, which is going to be the gradient at this point, times t. That's going to be the equation for the normal line. And it gives us that f of x, y, z, oh, actually, sorry. Yeah, so in this case, what was that g? That g is going to need to be a surface, but it gives us a surface as a function of 3 variables. We don't need that, that's for a different problem now. So we have this as a level set. Right, the set of all x, y, z such that this is equal to some constant, that's a level set. What we're looking for is the gradient of a level set, which is exactly what we have here. And that's why we did the z minus f of x, y, because it turns it into a level set. So it looks like I need the gradient. Let's go grab that gradient. Did not copy. Oh, come on, copy. This does not want to copy. 1 second. There we go. Okay, so we have our gradient. We need to evaluate it at -1, 2, 1. That's different from what we had, right? Yeah. So gradient of f at -1, 2, 1. That's going to be, so it's 8 and -4. Here we have -8 and 2. So that's plus. And then that's 8 and 2. So we have 4, -6, and 10. And this is my point, so r of t is just going to be -1, 2, 1 plus t times 4 -6, 10. Okay, so it says, though, determine the symmetric equations. So to remind you how this is done, um, in case you don't have it memorized, okay? So there's an easy way to memorize how to just write this directly into the symmetric equations, but let's write this as x, y, z. And I'll simplify this a little bit. So I have let's see, we have 4t minus 1. We have -6t plus 2. And 10t plus 1 equals x, y, z. So that gives me the parametric equations. X equals 4t minus 1. Y equals -6t plus 2. Oops, that's t plus 2. And z equals 10t plus 1. So what I'm going to do in each of these, I'm going to solve for t. So I have x plus 1 over 4 equals t. And I have y minus 2 over -6 equals t. And finally, z minus 1 over 10 equals t. And this gives me the symmetric equations. I have x plus 1 over 4 equals, because these are all equal to t, so this is y minus 2 over -6 equals z minus 1 over 10. And that's my answer. So if you know the point on the line, these right here are just going to be the negatives of those points, and below the denominators are just the components of your direction vector. So if you know those right away, you can just write it. So what's the point of giving us the level surface? So the level surface, right, it describes, first off, it describes a surface. Okay, so if we want to talk about a normal line, we need a surface. So why does it give us the level surface, though? So when we set this equal to a constant number, this describes a surface in XYZ space. If I just did f of x, y, z, and I just plotted this, this would be like a surface in like some 4D kind of space. So that doesn't really make a lot of sense for generally for Cal 3 though. So when he sets it equal to a level surface, that gives us, first off, it gives us a surface to work with. But the reason we want a level surface is because that the gradient of that function is going to be orthogonal to that surface. Okay, so basically this says that the gradient of f is orthogonal to whatever surface this defines. Okay, so if f is some surface like this, the gradient is going to be normal to that. This is the gradient of f, and this is f. So the gradient will be orthogonal. So that's what we want when we are solving problems like this with like tangent planes and lines normal to a surface. We want level sets to work with, so that way we can just take the gradient and get either our direction vector or our normal vector really quickly. Okay, last question. Oh, he didn't even give it in symmetric form. Okay, so those are the parametric equations, not the symmetric equations. Um, okay, part D is here. That needs to be a lot smaller, but not that small. Okay, and let's copy F. Actually, do I need F or do I just need the, I'm just going to need the gradient. So let me just copy the gradient. And we'll see why in a second. Okay, so calculate df dt. So df dt, you know what, no I don't, okay. That's going to be, so it's df dx times dx dt plus df dy times d. I guess this should be a full derivative because these are only functions of one variable. It makes no difference when you're actually computing it though. Dy dt plus df dz times dz dt. Or for a shorter notation, if I put r of t is equal to x, y, z, this is going to be the gradient of f at r of t dot r prime. Gradient of f dot r prime. All right, so let's go ahead and compute r prime. Let's do that first. So r prime of t is going to be 2t to 3t squared. So that's my r prime. Now I need gradient of f in terms of basically t. So I'm just going to plug in my x, y, and z into the gradient. So this is going to be 2 times 2t squared plus 4t squared plus 1, t squared plus 1, that's x times z, which is t cubed. And then I have 4t squared plus 1 times 2t plus 2z squared, 2t cubed squared. Then I have 4y times z, 2t t cubed, plus 2t squared plus 1 squared. Let's simplify this a little bit. So I have, let's see, 2 squared is 4. That's going to be 8t squared plus 4t t squared plus 1 t cubed. Don't think that'll simplify. No, it won't. And then I have, what is this? This is going to be 8t cubed. I can simplify that a little bit. I'll go back. T cubed plus 8t plus 2 t to the 6th. And here we have 8t to the 4 plus 2t to the 4 plus 4t squared plus 2. Alright, and simplifying it, this would be a lot easier to simplify if I had a specific numerical value, but here we go. So this is 8t squared plus 4t to the 5 plus 4t cubed. 8t cubed plus 8 plus 2t to the 6th. And we have 10t to the 4 plus 4t squared plus 2. Okay, so now we want gradient of f dot r prime. So we do the dot product, and so I'm just going to multiply these in my head, or kind of without writing it all out. So I have 2t squared times 2t, it's going to be 16t cubed plus 8t to the 6th plus 8t to the 4. And these all get multiplied by 2, so I have 16. And I'm doing the dot product, so these are going to be added instead of components of vectors. Plus 16t cubed plus 16 plus 4t to the 6th plus these all get multiplied by 3t squared, so I have 30t to the 6th plus 12t to the 4 plus 6t squared. Simplify. Let's see, so I have, what do we have? We have t to the 6, t to the 6, and t to the 6. That's 12, 42. 42 t to the 6. And then next we have to the 4. Let's see, so done with those. Then I have t to the 4 to the 4. So that's plus 20 t to the 4. And then I have t cubed, so that's plus 32 t cubed plus 16 plus, okay, so plus 6t squared plus 16. Let's see if that's right. I didn't copy the answer, or did he not put it? Let's see. Interesting. Okay, so let me copy this answer real quick so you can see how he put it. And I would never leave it like this. So he left it like this. And this irritates me for a lot of reasons. First off, because it's not in terms of one variable, right? So x, y, and z are supposed to be in terms of t. And it's kind of confusing when you mix the two like that, right? Because here we're saying that the only variable is t, but we have x, y, and z in there, which doesn't make a lot of sense. So, my opinion, always put it in terms of t. Right, any questions from that one? From any of those? Oh wow, we got quite a few people. I didn't realize so many people were here. How many we got? 16. So can we leave it like this? Like the answer that he gave? I guess. So if it's gonna be online, um, then it's probably going to have numerical values, so you would want to plug in the values that it gives you, meaning that you'd probably need it in terms of t if you're going to do that. But let's see, yeah, but I don't think that it's going to ask for like you to type it in like that, because otherwise it's going to be hard to check, what's equivalent and what's not. Okay, so next up, let's see, let me go back and see what we had asked for. Kevin had asked, was it Kevin? No, Hosea had asked for 7 and 8. So those are going to be up next. But let's see. How do you find the value of t from a given point x is 0? Like if that's so finding the value of t can be a bit difficult. Usually it would be the other way around. But for example, suppose they give you find the derivative this at the point 3, 1, 0. Okay, so I'm probably not going to be able to solve this, but let me just show you how this would work. So we have x, y, and z, t squared plus 1, 2t, t cubed. T squared plus 1, 2t, and t cubed. Right, so we want to find the t that satisfies this. And actually I have no clue if this isn't on there, so this would need to be also 0. I should find a harder point. Let's do one like this. Let's see. Let's do 1, 2, and 2. Okay, so what I would need to do is I need to set each of these equal to each other. So I have t squared plus 1 equals 2, 2t equals 2, and t cubed equals 1. And then from this, I need to solve for t. And make sure that the same value of t works for all the other ones. So here, this would tell me that t equals plus or minus 1. Okay, not sure which one I have. This one right here tells me that t equals 1. So, okay, so I have t equals 1. Let me check if that works up here. Yes, that works in the top one. T equals 1 down here. Yes, it works there also. So that's going to be my answer. And if they give me the value of t, and I need the xyz coordinates, so I don't have to do all this, I just plug them in to get to here to get the x, y, and z values to plug in to each of these values here. Right, so I could do this, or if maybe it said when t equals 3. Okay, so from here, I don't actually have to go and put everything in terms of t if it just wants this, because I can do what is x, y, and z. That's going to be 10, 6, and 27. So I can take those x, y, and z values and plug them in for each of these, and then I know t is 3. So that can save me a lot of time, so that way I don't have to go through all this process of simplifying and blah, 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 and putting it all in terms of t. If I know the x, y, and z values that I want to evaluate it at, I can skip that and just plug them in right away. Okay, any other questions from these? Let's see how long we've been going. Oh, wow. Okay, let's see, is Jose even here? Jose is here. Okay, so let's get to 7 and 8. Okay, so it looks like we're doing max and min problems. Oh, okay. So, Kevin, is this why you were asking? I'm looking at number 8. Is this why you're asking if we need to know absolute max and min because it's on the review? In the right chat. Yeah. Okay. Find the stationary points of f. So this is very simple. We look for the gradient and set it equal to 0. Just like um, just like you would in Cal 1. Find the derivative, set it equal to 0. We find the gradient, set it equal to 0. So step 1, find the gradient. This is derivative with respect to x. We're going to have 6 xy. That's 0 minus 6x plus 0. Okay. And then derivative with respect to y, we have 3x squared minus 4y minus 8. And we set this equal to 0, the 0 vector. Is that right? Yeah, that's right. Okay. So then that gives us two equations. We have 6xy minus 6x equals 0. And we have 3x squared minus 4y minus 8 equals 0. Let me move that 8 to the other side. No. Okay, fine, whatever. Equals 8. Okay, so if I work with this top one, I can factor out 6x times y minus 1. So this tells me that either x equals 0 or y equals 1. So I'll need to check both of those. If x equals 0, what do I have? I use the second one, and I have 0 minus 4y equals 8. Y equals minus 2, which gives me the point 0 minus 2. If y equals 1, plug that into the second one, I have 3x squared minus 4 equals 8. 3x squared equals 12. X squared equals 4. X equals plus or minus 2. So that actually gives me 2 points. I have 1, nope, I have 2, 1, and minus 2, 1. So these are my stationary points, the points where the gradient is 0. Let's check if that's right. I have those 3 points. Yes. For each stationary point, determine whether f has a local maximum, a local minimum, or a saddle point at P. Okay, so for this, I need to make the Hessian matrix. So this is the fxx, fxy, fyx, fyy. And then I'm going to need to evaluate this at each of these points and check the determinant. Okay, so I'm doing the x derivative of the x component. So this is going to be 6y minus 6. And then I do the x derivative of the y component here. So that's going to be 6x. This is going to be the same. And then the y derivative of the y component here, so that's going to be minus 4. Okay, so this h, it depends, again, h for Hessian matrix, it's just the matrix of second derivatives. It depends on x and y. Right, so it's going to be different depending on where we evaluate it at. And then depending on what we get when we evaluate it, we can determine if it's a local max or local min or a saddle point. So let's do each of these. At the point 0 minus 2, we have, so we're plugging in minus 12, that's minus 18. we have 0, 0, minus 4. So we have that the determinant of h is 18 times 4, negative 18 times negative 4. That's 18 times 4. And I don't care what it is right now. Actually, no, I do care what this is. Hold on. 18 times 4. Actually, I don't care what it is. All I care is that it's positive or negative or equal to 0. But this is clearly positive. Okay, so since this is positive, that means that this surface at this point is either a local maximum or a local minimum, like this. Okay, so now what I check is, technically what I should check is the trace when I add the diagonal components together, or I could just check one of them individually. That's what the book suggests. So I just look at fxx. So this means that local min or local max. Don't know which yet. So next I'm going to check the trace of h, and that's just what I get when I add the diagonals together. Not 14, just 4. This is clearly negative. Okay, and that's going to correspond to concave down. So it's going to be like this, meaning that our point is going to be a local maximum. Okay, so you also don't need to add these up. Again, the way the book does it, it just checks one component, and that's enough for these problems. You don't actually have to add them together. Okay, so let's see. Let's do 2, 1. That's going to be 6. Nope, that's going to be 0. 12, 12, minus 4. So we do the determinant. That's going to be 0 minus 12 squared, which is clearly less than 0. If the determinant is less than 0, this means right away, no extra checks, that this is a saddle point. Okay, done with that one. And let's check the last point, which was a minus 2, 1. So that's again 0. We have minus 12, minus 12, minus 4. This doesn't change anything. 0 minus minus 12 squared, still less than 0, saddle point. And let's make sure that those answers align. Yeah, so they're both saddle points, and that's a local maximum. Okay, so any questions on those? Yes, I'm going to get to those after I finish 7 and 8 from the review. Well, I'm going to go back and look at whatever ones you had asked me to do. Okay, so no questions on that. Okay, so next we have a Lagrange multiplier problem, right? It says to determine the minimum value of this subject to the constraint that we have this. Okay, so this is a different function. I should copy this down. Okay, so we have a maximum minimum problem, but we have a constraint. Okay, so that's when we use a Lagrange multiplier. Okay, so the way we do this is we have, we compute the gradient of f. Actually, first let me say that we're going to have g of xy. We're going to look at the constraint and make sure that it describes a level set. So that means all of the variables on one side and a constant on the other. Basically all the variables on one side. This is going to be all of the variables part. Okay, and now I'm going to set gradient of f equal to lambda times the gradient of g. So that means I need to compute the gradient of f and the gradient of g. Gradient of g, that's easy to compute. This is 2, 3. That's nice and simple. And the gradient of f, not as simple, but this is going to be 4x plus y, and then x minus 2y. Okay, and don't forget that I still have this constraint. It always holds. So I set these equal, and I have, I'm going to do this in columns. It's a little bit easier to see. I have 4x plus y and x minus 2y equals 2 lambda and 3 lambda. Okay, so first thing I do, well, actually this tells me that I have three equations. I have 4x plus y equals 2 lambda. I have x minus 2y equals 3 lambda. And I have 2x plus 3y equals 16. Right, so I have three equations, three unknowns. So I start solving. Let's see, first I'm going to solve for lambda. I'll just divide both sides by 2 and plug that in here. So I have lambda equals, that's going to be 2x plus 1/2 y. And I plug that in, so I have x minus, what did I say, 2y? Yeah, 2y equals 3 times 2x plus 3 over 2y. Let's solve for x and then plug that into the other one. So I have x minus 2y equals 6x. Did I already distribute the 3? Yeah, so that should be 1. Yeah, plus 3 over 2y. Subtract 3 halves y and subtract x from both sides, so I have minus 3 halves y. Can't think right now, so this is minus 4 over 2y minus 3 over 2y equals 5x. That tells me that x equals minus 7 over 10y. Now I take that and I plug this into this one. So we have 2 times x, which is minus 7 over 10, y plus 3y equals 16. Those 2's cancel, that's a 5, and I get minus 7 over 5 plus 15 over 5, y equals 16. This tells me that I have, what is that, 8y, 8 over 5y. Solve for y, and I have y equals 10. Okay, and then I know that for this particular system that's going to be the only point. Well, okay, actually, hold on. So I have y equals 10. I still need x. This tells me that x equals minus 7. So point minus 7, 10, is a critical point for this function, or it's the minimum value for this function. It's the only stationary point, so it has to be. I guess if it's asking for a minimum, it's going to be this. Actually, is that true? Hang on. If this goes to infinity, yeah. No, wait. Okay, so this. Okay, so I guess it depends. I'm assuming that this is referring to a local minimum. I'll assume that it's referring to a local minimum, but this is the line. This is the line. Um, y equals what is that? 16 minus 2x over 3. If we were to plug that in, could we get a minus infinity? No. That would go off to positive infinity. Okay, yeah, so that's the minimum. And let's see if that was the answer. Wait, where's my question? Where's the question? There it is. Oh, that's the point where there's the minimum. It says determine the minimum value, so I still need to plug that into the original function. Okay, let me just check yeah, so at negative 7, 10. So I still need to plug that in, so I'm going to take that, I'm going to plug it into this function. Can I fit that on screen? Not quite. Okay, so I still need to plug in to find the actual minimum. F of minus 7, 10. So that's 2 times minus 7 squared plus minus 7 times 10 minus 10 squared plus 1 equals, this is minus 70 minus 100 plus 1 plus 49 times 2. 49 times 2 is what? 98? Yes. So that's going to be negative 1 minus 70 equals negative 71. Okay, any questions, Lagrange multiplier? So this one was nice because I only had one value for lambda and one value for x and y. That ended up because it was all a linear system at the end. Okay. Let's see. So I'm going to go ahead and do number 8. Kevin, I know you said you had some questions. Can you go ahead and post them in the chat so I can have them when I'm done with this one. Also, if anybody else has questions or topics they want to go over, feel free to post them in the chat. So this one is on absolute maximum and absolute minimum. That's not fun. Why are there two? That's even worse. Why are there two? That's even worse. Okay, fine. So this is number 8 from the review. Find the absolute maximum and okay, so first thing we need to do is find the local max and local min. That's going to cover the inside part. And then we need to check also on the boundary. Okay, so first we do local max, local min. Let's do the gradient of f, which is going to be 2x minus 2, and gradient or derivative with respect to y is going to be 4y. That's it. Set that equal to 0. We get that 2x minus 2 equals 0, and 4y equals 0. That's pretty easy to see. We have x equals 1, y equals 0. So we're looking at the point 1, 0. Okay, we need to do the same thing as before. We need to know if this is a maximum or... no, you know what? We don't need to do that. Now I need to find the maximum and minimum values on the perimeter. So I could do this two ways. I could do this as a Lagrange multiplier problem. So I need to find the minimum and maximum values of this function on the boundary. So I could do this two ways. I could either do the Lagrange multiplier problem, or I could parameterize the edge, the boundary, and then just do the derivative with respect to the parameter. That second one sounds like it'll be a lot faster for this one. So that's what I'm going to do. Just know that I could also do it using the Lagrange multiplier method. So I'm going to parameterize the boundary as 2 2 cosine t, 2 sine t. Right, so this is the parameterization for the boundary of this, right, when this is equal. So so let's plug these into this function. Can I fit both? Yes, I can. So I have f of t is now 2 cosine t squared plus 2 times 2, let's see, 2 times 2 sine t squared minus 2 times 2 cosine t plus 2. So f of t, I simplify a little bit. This is 4 cosine squared t plus 8 sine squared t minus 4 cosine t plus 2. One more simplification. This is going to be 4 plus 4 sine squared t. Right, 4 cosine squared plus 4 sine squared is 4. So that's here. Then I add the 2, so that's going to become 6 minus 4 cosine t. Now I do the derivative, like usual, of f with respect to t, like Cal 1. So that goes away. So I have 8 sine t cosine t minus derivative of cosine is negative sine plus 4 sine t. Set that equal to 0. Factor out the 4 sine t. And I have 2 cosine t plus 1 equals 0. This tells me that either sine t equals 0 or cosine t is 2 times cosine t plus 1 is equal to 0, meaning that cosine of t is equal to negative 1 half. So this means that t equals 0 or pi. This tells me that t equals, let's see, so negative, that's going to be 2 pi over 3 and 4 pi over 3. Okay, now I need to plug these values of t in to get the actual values and figure out what is the value at 1, 0. I can do that real quick. Let's just do this down here. F of 1, 0. I should copy this function. Okay, so our local max or min, we don't know what it was, but it was 1, 0. So f of 1, 0. That's not the right function. Eraser. That was not the right function. I hope I did this. Yeah, okay. I just copied the wrong one there. Okay, f of 1, 0. What is this? This is 1 minus 2 plus 2, which is 1. Now I need to figure out what is f of t equals 0. That's the same as f of 4 cosine 0 for sine 0, right? Because that's what the parameterization was, which is just f of 4, 0. So if we do this, then if x is 4, this becomes 16 plus 0 minus 8 plus 2, so that's 8, 10. Okay, so that's looking like the max so far. How did I get 6? Where do you see a 6? Oh, okay, the 6. I did 4 cosine squared plus 4 sine squared plus 4 sine squared, and then I have the plus 2 at the end. So this cosine squared plus sine squared is 1, so that's going to be 4 plus 2 is 6. And then I have the 4 sine squared left over. Where was I at? Plugging this in. So we got 10. So that's the maximum so far, and that's the minimum so far. We can do the same thing for pi. And also, when I'm doing these, I could just plug t in to each of these, but I feel like that would be more work right now. Well, it's the same thing. So at pi, we're going to have f of minus 4 and 0, which is going to be, that's still going to be 16. It's going to be plus 8 plus 2, which is 26. Yes. All right, so that's the maximum so far. We still have these other ones that aren't going to be fun to work out. F of t equals pi over 2 pi over 3. That's going to be the same as f of 4 cosine of 2 pi over 3, which is negative 2. And sine is root 3 over 2. So 4 times root 3 over 2, that's going to be 2 root 3. Right? Okay. So we plug this in, and what do we get? We have 4 plus 2 times 4 times 3 minus plus 4 plus 2. Yeah. Okay, so that's 8, 10 plus 24, which is 34. All right, that's the maximum so far. And finally, we do f of t equals 4 pi over 3. So we get f of 4 times minus 1/2, which is minus 2. And 4 times sine root 3 over 2, minus root 3 over 2. That's minus 2 root 3. So this will be the same, because we square the y, so the negative sign doesn't make a difference. So this is going to be 34 as well. So min at 1, 0 with f of 1, 0 equals 1. And max at f of minus 2 plus or minus 2 root 3, which is 34. Okay, so that's the absolute max and absolute minimum over this domain. Any questions on that? I know those are long and tedious. There's still another one, another example. Let's see how many people we got right now. 14, and what time is it? Dang. These problems are so long, time just flies. Okay, so let's go ahead and do this last one, and then we'll move on to some flux problems. Oh wait, what? At 0, 9. How did I get 9? Oh, that's the wrong one. Yeah, okay. Plus or minus root 3. I'm going to say that's not right, because that's not on the boundary, and I don't know, there's only one interior critical point. No, I parameterized it wrong. Oh my gosh. Oh my gosh. Wait, no, that's right. That's right. I did 2. Yeah, okay. Chat wants to move on. Okay, so move on. Skip question. Skip part B. Can I get a second? Cool. All right. Let's see. So Kevin had requested a flux problem. Let's see. Okay, so here's the question from Kevin. Compute the flux of the vector field out of the pillbox. I don't know why they call it a pillbox. It's like, okay. I mean, I know why they call it a pillbox, but it's such a weird term to call it. So it's just describing a cube like this. Um, wait, what? Hold on. A pillbox is supposed to be squared. This is a cylinder. What on earth? Why do they call it a pill? Whatever. Whatever. Okay, so we have a cylinder with radius 3 and a height of 2. Okay, so it says compute the flux of the vector field V equals this. So what it's asking, if this is the surface S, compute over the surface S, compute F dot, nope, V dot ds. And we're integrating over the entire surface. So I can write it like this because we're integrating over the entire surface, right? It's a closed boundary. There's no real edge. You know, if I'm walking along the surface, I'm never going to get to the edge of this, right? I can always just go around. So this is a closed surface, and this is integrating with respect to S, like this. So just a reminder what that means. It also means, so same thing here, v dot n ds, right? So now I have a scalar function that I can actually integrate. The same thing. I prefer this notation. Actually, I don't know which one I prefer, but it doesn't matter. The point is, if we use the divergence theorem, this becomes really easy. I can change this into a triple integral over the region that's inside, right? The contained region. So I just need to figure out the bounds for that. And then I'm integrating the divergence of v dv. So it's going to be dx, dy, dz. Okay, so first thing I should do is compute the divergence. The divergence of v is x squared plus, actually, let me actually write this out. That's going to be dv, the x component, dx. Yeah, one second, Rodolfo. Dv, dy. So I'm going to, I should be able to post this right after I'm done. Looks like we have enough problems that I don't have to edit. So I'm going to post this right after I'm done. It'll probably take a little bit to upload. So I'm going to say it's probably going to be up by around 11. I don't know how long it'll take to upload, but probably around 11 or so. Okay, so real quick here, these x, y, z little subscripts, they don't mean derivatives. Here they mean the components. So the I component, the j component, and the k component. So this is going to be x squared plus y squared plus 1. Okay, so this is what I want to integrate, and now I need to set up the bounds for this. But this actually looks, okay, so this looks like it would be a lot easier in cylindrical coordinates. So that's actually what I'm going to do. I'm going to do this in cylindrical coordinates. So when I integrate over this region, we do one at a time. We have the radius going from 0 to 3. So we have radius going from 0 to 3. Theta goes all the way around, 2 pi bigger than or equal to 0. And then z is between 0 and 2. So I can set up the integral from 0 to 3, r squared plus 1. Don't forget to multiply by r dr. Then from 0 to 2, dz. And then from 0 to 2 pi d theta. So this is separable. I can integrate this. I can separate this into 0 to 3, r cubed plus r dr times 0 to 2 dz times integral from 0 to 2 pi d theta equals, that's going to be r to the 4 over 4 plus r squared over 2 from 0 to 3. This becomes 2, and this becomes 2 pi equals, I can fit that on that page, that's 4 pi times 3 to the 4 is 81 over 4 plus 9 over 2. Those cancel. So that's going to be 18 over 4. So the 4 cancels, and I get 99 pi, like that. Pi. Okay, so questions on divergence theorem. So this one, if I'm integrating over a closed surface, I can take this flux integral, right, where I'm doing v.ds, and change it into a regular triple integral, where I'm integrating the divergence. Yeah. So for example, an example where this wouldn't work is if you had the surface f of xy, say something like x squared plus y. All right, so this describes a surface kind of in like a 2D space, right? We have the xy on the bottom, right? We have the xy on the bottom, and then we kind of have this surface like up above. This wouldn't work, okay? Because there's clearly, it's not closed, right? It's not a closed surface. It's not going to, it doesn't enclose an area. So think of it that way. Your surface needs to enclose an area for this to work. Otherwise, what's the triple integral that you're going to use? Okay. Yeah, let me finish this other one from Kevin, and then we'll get to number 4. And I assume you mean from the review, right? Yeah. How much time do we got? Yeah, we should have time. Okay, compute the integral. Oh yeah, I can see why. The line integral. Okay, so this one, it gives us a line integral to compute, and it says it's easy, it's less work with Stokes, and I agree, but let's just see why that is. So um, the region, the curve that it describes, right, from 200 to wait, what? Hold on. Okay, so this is 3D space. From x is 2 here, and it goes to where y is 2, so that's over here, to where z is 2. Oh, okay, I see. So it describes a triangle. I see. Um, here, back to here. I see. Okay. Um, so let's just say what is this with Stokes? With Stokes theorem, this line integral, right? Because we're integrating along a closed surface, this becomes um, the curl of v dot ds. Right? Yeah. Okay, so I don't know if this is necessarily simpler, but um, we'll give it a go. Oh, yeah, it is. Yeah, it is. I see. Okay. So what is the curl? Let's set this up. So we have I, J, K, d, dx, d, dy, d, dz, and I have 3x minus y, 6x here. Okay, so I do the determinant just like normal. So I cross this out, and I have 6 d dy of 6x minus d dz of minus y. That's clearly going to be 0. And then we cross out the middle one, and we have d dx of 6x minus, and we have minus here, so that's going to be minus out here. There, and then minus d dz of 3x. And finally, we have, cross this one out, we have dx of y minus d dy of 3x. Okay, so we have a lot of things that cancel out to 0. That's 0, that's 0, that's 0, that's 0, that's 0. So what we're left with is 0 minus 6, 0. That's what the curl is. And what I'm going to use is, do I want to do parameterization? Um, I'm going to write the equation for this surface. So I'm going to parameterize it. So I know that, so let's see. I can write the equation for this plane actually rather quickly. I'm going to do this to save some time, but I know that the normal is going to be 1, 1, 1, right? Because all of these points are evenly spaced out, and it'd be the same as if it just went through 1, 1, 1. and it's going to have to be this. So this is going to be x minus 2 plus y minus 2 plus, wait, hold up. I need a point on the plane. So let's just do z equals. So to write the equation of a plane, I need a point on the plane, and my point is going to be 0, 0, 2. So I have 1 times x plus 1 times y plus 1 times z minus 2 equals 0. So I can have z equals, what do I want? I want 2 minus x minus y. Yeah. Okay, so I can parameterize this. R of u v is equal to what? This is going to be u v 2 minus u minus v. And also, to save myself some time, what I can do is, well, actually, okay, so here we have that x goes from 0 to 2, y goes from 0 to x, 2 minus x. Right, that describes kind of this region right here. Okay, and then I don't believe for 1 second that Stokes' theorem was faster, because surface integrals are never fast. I mean, yeah, you would have had to broke it up into 3 parts and integrated along each of them separately. So you would have had to parameterize this curve, parameterize that curve, parameterize that curve. It would have been a pain, but this is still a pain. Okay, so I need to compute RU. The derivative of R with respect to U, or dr du. This is the vector 1, 0, minus 1. RV, which is 0, 1, minus 1. RU cross RV, which is ijk 1, 0, minus 1, 0, 1, minus 1, which is, cross that out, we get 0, minus 1, we got 1. Cross that out, we get minus 1, minus 0. That's also going to be 1. Right, we have the minus there. Cross this out, we get 1 minus 0, we get 1. Right, like I said, we know that this is the normal. Oh. No, we're good. Okay, so then to integrate over the surface, this function, was it f or v, whatever, it's curl of v. Dot ds. This is the same as the integral over s, so nope, I'll say over d, which is this region here, right, the u and v, sorry, this should be u and v. Curl cross v dot RU cross RV dA. All right, so that means du dv. Y'all, I've gone through 11 pages of stuff so far. That's crazy. Okay, let's copy this down. We had curl v, which was 0 minus 6, 0. Yeah. And we had RU cross RV, which is 1, 1, 1. So what we're integrating is we're integrating from 0 to 2 minus v, nope, 2 minus u, the dot product of this, which is just minus 6 dv, integral from 0 to 2 du. This becomes minus 6 integral 0 to 2 minus u du, minus 6 times 2 minus u. Oops, no, I'm integrating this. So this is 2u minus u squared over 2 from 0 to 2. And that gives me minus 6 times 4 minus, that's 4 over 2, that's 2, minus 12. So, was that less work? I don't know. Maybe less opportunities to mess things up. I don't know. But yeah, so minus 12 was the answer. So just to recap what I did, I had a line integral. I used Stokes' theorem to write this as integral over some region of the curl of v dot ds. But I know that that's the same as, when I parameterize it, this is the same as integral over the contained region, or the parameterized region of curl v dot ru cross rv dA. Yes. Yes, but I was a little bit nervous about finding the area of that region. So I don't know, like, I mean, it is a triangle, but I feel like that'd be really error prone to try to try to think about the area of it. So you're totally right, and I could have just actually I could have done that once I did the normal and I knew the curl was constant. Yeah, I could have just done the dot product and multiplied by the area of that surface if you're confident you know what the area of that surface is. So I worked a problem like this the other day and I totally got that. Let's see, so how can I figure out how to parameterize what? Parameterize the lines or the surface? Okay, so what I did was, since this is surface, I know that I can write this as like z equals f of xy, right? So I know that's possible. So what I did was I just wrote so when we parameterize a surface like this, we can always just do the parameterization u v f of u v. And that will give us a perfectly fine parameterization. Um, there's other times where when you have like a sphere or something, that it might be easier to do something else, but you can always start with this and then change variables if you need to. I was saying, so Diego, I worked one of these problems the other day for someone, and I totally made that mistake where I forgot to multiply by the the area of that surface. Or actually, I just completely got that area wrong. So I know this, I won't make a mistake because it's the same procedure as any other one. Okay, any other questions on Stokes' theorem, divergence theorem? Otherwise, I'll move on to Vanessa's request for number 4. Okay, chat is quiet, so I assume that we can move on. Okay, problem number 4. Let's see, a curve C in the plane defined by the parametric equations. Find the length. Okay, so arc length and find the curvature. Man. Okay, vector function determines a curve. Okay, find the unit tangent vector, the principal unit normal vector. Determine the curvature. Determine the tangential and normal components of the acceleration vector. I see, okay. It has been so long since I thought about curvature. It feels like an entire year ago. Nah, not a year, just a semester. What's going on? My mouse is being weird. Okay, copy parts of this. Okay, so this is parameterization, and we want to find the arc length from 0 to 2. So if you recall, arc length, we're integrating over the curve. It's just this. So in terms of line integrals, it's that simple. Okay, so we're integrating 1 with respect to ds. So let's see if I write r of t is xy. This becomes, just like we do any other line integral, this is the integral from 0 to 2 of norm r prime of t dt. So r prime of t is equal to what? 2t for t squared. And the norm of that, square root of 4t squared plus 4t squared times 4t squared. So I can factor 4t squared out and I get 2t root 1 plus 4t squared. Okay, so that's what we're integrating from 0 to 2. 2t root 1 plus 4t squared dt. And I hope that this makes a lot more sense in context of the line integrals that we've done, because that's really all this is. Okay, I'll do a u substitution. U equals 1 plus 4t squared. Du equals 8t dt. So I need to multiply and divide by 4. So I get 1/4 integral from, let's see, at 0 this is 1, at 2 I have 17. And then root u du equals 1/4 u to the 3/2. Nope. Yeah, Diego, can you go ahead and post the question? Actually, you know what? Let me. Sorry, 1 second. I'll get back to the problem in 1 second. Let me change the permissions real quick so that you guys can post pictures. Edit channel permissions. Let's see. So I'll just put it for everyone. Okay, can you go ahead, Diego? Can you go ahead and post the question on the chat? Okay, so this is what? That's u to the 3/2, so it's gonna be 2/3. U to the 3/2 from 1 to 17. So the 2 cancels and we get 2, so we get 1/6 times 17 to the 3/2 minus 1, which looks correct. Yep. Okay, so the next part was find the curvature at t equals 1. So find the curvature. So if you remember the curvature, that was the rate at which, so we have this curve, we have the tangent vector. That was the rate at which the tangent vector was changing. So it was dt ds. Okay, and then we had that we use the chain rule, so this is dt dt times dt ds. So we just use this times dt ds, and we use that this is the same as 1 over dt dt over norm ds. Well, actually, that's not a norm, that's a scalar now, so that should be absolute value. No, never mind, it's should be norm. Cool, thanks. Okay, so dt. And ds dt, what is that? That's going to be just the norm of r prime. Okay, so we need to do a couple things. First, we need to find the unit tangent vector, and then find the derivative of that. In the process, we'll find r prime, and we need to find the norm of that. This was the curvature. So real quick, notice I started from the definition, right? It's the rate at which the tangent vector is changing, dt ds. So that's honestly, that's all I remember right now because I do not remember the formulas and I had to derive this to remember it for myself right now. So if you can remember this and then just remember to kind of these couple steps, it's a lot less memorization. but if you memorize the formulas, good on you. Okay, so the tangent vector, let's remember what that is. That's going to be the derivative of r normalized. So what is r? We have r right up here. I'm just going to copy this. Let me. What is going on? Okay. Okay, so r, what is r? R of t is, and we did this up a second ago, but this is t squared plus 1 4/3 t cubed minus 1. So that means that r prime is 2t plus, no plus, comma, 4t squared. And we're going to need the norm of that, so let's go ahead and compute that right now. This is norm of r prime. We did this already. This is 2t root 1 plus 4t squared. Okay, so the unit tangent vector is going to be t squared plus 1, nope, 2t over 2t root 1 plus 4t squared, and then this. Ew, we have to differentiate this? That's gross. Okay, so here it cancels. How do I want to do this? So, because I need to find the derivative of this. I think the fastest way to do this is write it like this. So I'm going to factor out the 1 over... No, you know what? I'm going to do it like this. I'm not going to cancel that out. I'm going to factor out 2t... Nope. Don't want to do that either. Cancel that out. 1 plus 4t squared times 1, comma... So it's going to be 2t squared over 3 minus 1 over 2t. Okay, so now when I do the derivative of this with respect to t, I just have to do the product rule. Okay, so derivative of this is going to be, what is that? Negative 1/2 1 over 1 plus 4t squared to the 3/2 times this big thing. Plus 1 over root 1 plus 4t squared times the derivative of this. So that's going to be 0. That's going to be 4t over 3 minus plus 1 over 2t squared. Okay, and we could combine these, but does it want it at a specific value of t? Yeah, t equals 1. So t equals 1. So I can just plug t equals 1 in, and this gives me, what? Minus 1/2 times 1 over 2 to the, nope, 1 plus 4 to the 3/2 times 1, we have 2 over 3 minus 1/2 plus 1 over, again, 5 to the 3/2, 0, 4/3 plus 1/2. Okay, so now I'll distribute the negative 1/2. So we have 1/5 to the 3/2 times minus 1/2 plus 0. And then we have comma minus 1/3 plus 1/4 plus 4/3 plus 1/2. Right, so I just combined the two vectors by distributing the negative 2 inside and leaving the 5 to the 3/2 factored out. Those combine for 1, so I have 1/5 to the 3/2 times minus 1/2. That's 3/4 and 1, so that's 1 3/4, 7/4. Okay, simplified all that. Now I need the norm of it. So how do I want to do this? Let's go ahead and distribute that. So we have, so this is t dt at t equals 1. That's negative 1/2, 5 to the 3/2, and 7/4 times 5 to the 3/2. Okay, so we need the norm of that, and then we'll basically be done. This is square root of each of these squared, so that's going to be 1/4 times 5 cubed plus 49/16 times 5 cubed. Looks like we'll have some simplification, so we'll have 4 plus 49/16 times 5 cubed. That's 53 on top. I can pull out the 16, so we have 1/4 root. I can pull out. See, I can also pull out a 25, so I have 1/20. 53/5. Almost done. So that's the rate of change, norm of rate of change of my tangent vector with respect to time, or the parameterization t. Then I just need to divide by this. But we also need that at 1, which is 2√5. So my answer, the curvature over norm r prime is, let's see, that's going to be 1/20 root 53/5 over 2√5. So this is, let's see, if I simplify this, this is going to be multiplied by 1/2√5 times 1/2√5. It's 1/40 times 1/5 times root 53. What is that? That's root 53/200. I hope that's the right answer. Root 5/25. Where did I go wrong? Y'all got any comments? Where do you think I went wrong? probably a small mistake somewhere in here, like when I plugged in. So it's, oh, it's right there. Oh my gosh. Y'all see it? So here I plugged in r instead of r prime. So this actually should have been 4t squared. So those cancel and makes this a lot simpler. So I factor that out and we get 2t. Oh my gosh, that means so much of this is wrong. This is going to be 2t. And this will just be 2. Okay, so we plug in 1. That stays like that. This becomes a 2 though. This is also a 2. There, so this is a 2 and a 2. No, hang on. So I distribute the negative 1/2, so we get -1 here and +2 here, which gives -1/2 and 1. It's just a 1 here. Okay, and then we put that in, so this becomes, this goes away. So 1, put over a common denominator of 4. So that's 1 plus 4 over 4. Oh, I see. Okay, so that's root 5, or that's going to be a 5, so that's going to cancel. So we're going to have 1 over, I can bring out a 2 and bring out a 5. Okay, so then this whole thing up here becomes 1 over 10 over 2 root 5. And I'm still off slightly. All right, let me check how much I'm off by. Equals 1 over 20 root 5. What is it supposed to be? See, r prime is 2 root 5, okay. Well, okay, so I put this as, so this is equal to root 5 over 100. So I'm off by a factor of 4. I'm missing a 4 somewhere. Okay, but I think you'll get the point. So, there it is. I forgot to use the chain rule. So here I should have multiplied this by yeah, so I do, let's see, wait, so I did this, yeah, so the derivative of this term should have had, should also be multiplied by 2t, no, 8t. right? Because I use the chain rule from here, and that cancels, and that gives me my 4 that I was looking for. Okay, so I'm not going to go back and fix this, but it's a small mistake right there. Okay, the next one, find the unit tangent vector. So much time I got. Okay, I can do this last one more with curvature and tangent vectors and stuff. But I want to see, does anyone else have any questions that they want to see? Um, okay, so you want to see the part 3 one. Okay. Okay, anyone else? All right, so I'll go ahead and copy this down, and we'll get started on the part B. Okay, so let's go ahead and we're gonna need the tangent and normal. Like we're gonna have to go through all of this to get to the last one because we're gonna need the tangent and normal to begin with. What's going on with my mic? There we go. Can you all hear me? Okay. Um, what was gonna? Oh, here we go. R. Let's see. Am I streaming? Hold on. Let me check my stream settings. That should be good. Okay. R prime. That's gonna be 2. Derivative of sine is cosine. Derivative of cosine is negative sine, so it's gonna be plus 2 sine 2t. This is root 5. So the norm of R prime is 4 cosine squared 2t plus 4 sine squared 2t plus 5 equals cosine squared plus sine squared is 1, so this is 4 plus 5, it's just 3. So that means that the unit tangent vector is 2/3 cosine of 2t, 2/3 sine of 2t, and root 5 over 3. The normal vector was dt over norm. Let me write it as prime. So that's t prime over the norm of t at prime. So that's going to be the normal. So t prime, derivative of cosine is negative sine, so that's going to be minus 4 over 3. Cosine is sine, negative sine. Derivative of sine is cosine, so it's going to be 4 over 3 cosine of 2t. That's 0. Okay, and the norm of this is what? Well, that's just, I can do square root, but it's just going to be square root of this squared plus this squared. That's just going to end up being 4 over 3, meaning that the normal, when I divide this through, is going to be negative sine of 2t cosine of 2t, 0. So those are my tangent and unit normal, and normal components. Okay, so here this is t prime. So for my curvature, right? Remember what I did before? I did the norm of dt dt. Right, this is this right here. That's just t at prime over r prime. Right, this is the norm of t prime over norm r prime. R prime we saw was 3, and norm of t prime we computed right here. That's 4/3, which is 4 over 9. Is that right? I didn't copy the answers. 4 over 9, yeah. Okay, so there's a number of ways to do this, to do the this next question. Let's see, how much time do I have? Okay, so we can do r double prime. Well, what is that? That's the derivative of r prime. But what is r prime? That's the same as norm r prime times t. Okay, so if I was to do the derivative of this, what I would get would be d dt of this r prime times t plus, so this is just the chain rule. So this plus norm r prime times derivative of t, which we know is, well, which is just t hat prime. So this becomes, let me just leave it like this, because that's going to end up being 0. Plus, okay, so this we know is the same as r prime times the norm. Actually, yeah. If I multiply and divide by t hat prime, this is just the unit normal. And actually, real quick, so we know that r prime in our question is going to be a constant. It's going to be 3. So the derivative of that with respect to t is 0. So this is going to be 0 plus, and I'll show you guys another way to work this that may or may not be simpler. But let me write this as v prime. So v would be for velocity. You know, it's r prime, the norm of r prime. Here, we know that if we, or I know that if we square this and also divide by that, like this right here is the curvature. So I have v prime t plus v squared times the curvature times n. So v, what is v? V is the norm of r prime, right? It's the speed. So we know that v is 3, so this is going to be 0, right? Think of this as the rate of change at which you're speeding up. And here, this is the angular acceleration. Or, yeah, the angular acceleration. If you've done physics, this is the same as like v squared over r, where r is the radius of curvature. So that's where that comes from. But we know that this is going to be, so that's plus, so that's going to be 9 times, what do we say, 4 over 9? Yeah, 4 over 9. Those cancel. So our tangential component, AT, is going to be 0, and AN is going to be 4. So let me show you guys another way to do this. That in some cases is faster. This case wasn't actually that bad. I showed a bunch of extra steps. But since we had the curvature and the velocity, it was really easy to compute. But what we can also do is if we just start with r. What was r? I don't even remember. Oh, there we go. If we just start with r and we take the second derivative with respect to t, we can just do the projection onto the tangential and normal vectors. Where'd my pen go? I just had my pen. There it is. Okay, so this is the second way of doing it. R double prime. So I do the second derivative, that's going to be negative 4 sine of 2t. It's going to be positive 4 cosine of 2t, and that's going to be 0. Okay, so I can do the projection of this onto the tangent vector and the normal vector. So the projection onto the tangent vector, if you guys remember, this is the acceleration, I'll call this A, dot the tangent vector over the norm of the tangent vector. Well, so the tangent vector is already a unit normal vector. Or yeah, not unit normal, is already a unit vector. So this is 1. So actually AT is just going to be this. So AT is just the dot product of A dot the tangent vector. So A is the second derivative. So if I know the tangent vector, which I do, it's this. I can copy that. Okay, so I know the tangent vector. Does it not going to let me move it to the next? Okay, so I can do the dot product. So I have A dot t is going to be minus 8/3 sine 2t cosine 2t plus 8/3 cosine 2t sine 2t plus 0. Those cancel out and give me 0. Then I can do the same thing for the normal, and I could do the projection. I could do a dot n, and that would work. Or I could also just do an is equal to, or I could do a, actually, start like this. I know that a equals a t this, and since these two vectors are orthogonal, that means that norm of a squared, we have Pythagorean theorem, it's going to be a squared plus an squared. So if I want an, I could either do the projection onto the normal, that's always going to work, or I can just do an equals square root of norm a squared minus at squared. So we're just kind of subtracting off the tangential component. So that's 0. So here an is going to be the same as just the norm of a. So norm of a is going to be 4, right? Sine squared plus cosine squared, that's going to be 4. So that's just 4. Okay. What time is it? Any last questions? If I go much longer, you guys are going to start hearing my stomach on the mic. I gotta go find dinner. Chat's really quiet. Okay, roll's good. Oh, that's right, Diego, you had one. Sorry. Find the mass. The mass density is. Okay, this is a quick one. I'll do this one. Okay. Let me copy this. Okay, find the mass of a ball of radius 2 centimeters if the mass density is 3 times the distance to the center. Okay, so what this is describing, so we have a ball, and it's got its center, let's just say the center's at the origin, and the density, it depends on how far out it is. So rho, yeah, we're gonna do this, what? That's annoying. Okay, I'm gonna use D for density, even though that's like almost never used. They always use rho for density. But since I'm using spherical coordinates also uses rho. So what this says is that the density of the mass is 3 times the distance from the center. So in spherical coordinates, the distance from the center, from the origin, is rho, right? Rho being the distance from the center. So the mass, find the mass of the ball. So basically I want to integrate this mass, right? So that's the mass at a tiny point. So I want to integrate that over this whole sphere. So to integrate a whole sphere, I'm integrating from rho going from 0 to radius 2. Rho squared sine phi d rho. And then phi goes from 0 to pi. Right, so if this is z, this is x, phi, it starts here and it goes all the way around to here. So from 0 to pi, and theta goes all the way around, 0 to 2 pi. So I can, I know you said you just need to set it, but I'm going to go ahead and solve it. Let's see, so you did that. Let's go ahead and integrate it and see what we got. So see what we get. Separable, so I get 3 integral rho cubed from 0 to 2 d rho, and then integral 0 to pi sine phi d phi, integral 0 to 2 pi d theta. Okay, so this right away is 2 pi. So what I have is 6 pi times rho to the 4 over 4 from 0 to 2. Integral of cosine is negative, sorry, of sine is negative cosine phi from 0 to pi, which gives me 2, 4, 8, 16 over 4, that's 4 minus 0 minus cosine of pi is negative 1 minus cosine of 0 is 1. So I have, let's see, that's 2 times 4 is 8, and I get 48 pi. And that wasn't the answer? Answer 144. Answer 144. What? Yeah. Actually, you know what? Let's just let me check. I think there's an easy way to check that this is absolutely wrong. So the radius, let's just assume that it has a constant density of 6, right? 3 times the maximum radius. So if the density was constant at 6, then it would be 6 times the area, which is 4/3 pi r cubed. So first off, there should be a pi in there, but 2 cubed. Okay, so roughly speaking, we have 8 times 6, which is 48. Those would roughly cancel. What's 48 times 4? Okay. Let's see what that is. Equals. Yeah, maybe. Let me just see one more thing. If we did 4 times 48. Okay. Yeah, no, okay, so 144 is still within the bar. Oops. Yeah, so we're gonna say that that's wrong, and because that's actually a somewhat simple question, so I don't. Okay, I can't erase that. There's not really a lot of room for it to be wrong. Was that on the review, or where was that question from? Oh, that was on the second review. Okay. So yeah, I'm gonna say it's wrong. 48 pi is my answer, and I'm sticking to it. All right, feel free to post them. I think he read the A as 6 and plugged into the calculator. Who knows? Yeah, who knows? Hopefully, all can see that working these problems takes a long time, even if you know the stuff. All right, so the final's tomorrow, right? Or it opens up tomorrow? Yeah, okay. So I'm gonna go ahead and cut this off.